All right, good morning, everybody. Today is Codeforces Raif round 1, which I think corresponds to round 676. And this will be rated for me, so it's a Div 1, Div 2 combined. I think this is going to have... No, this is just its own round, I guess. So it's, I guess, similar to a global round then, because it's rated for both people and everyone's in the same round. So that should be fun. It's going to be rated for me, which means the commentary will be on the lighter side. But if you're interested in solutions, I'll have all of those at the end. So you can skip the end of the video. If you're looking for solutions to a particular problem, there'll also be timestamps in the description. So hopefully that's helpful if you're looking for those. Otherwise, it should be a fun contest. It's by some new authors. I'm not really familiar with them. It's possible they work for Raif, but never know. If you're competing, good luck, have fun, and I'll see you on the scoreboard. Ready, go. X1 is a rope. So Manhattan distance plus 1 maybe. Yeah. Let me... what? Oh, plus 2. Because you have to go around the corner. Yeah. Makes sense. I'll draw a picture out in the editorial, or my solution to it. Got it. In the snake exhibition, there are n rooms, numbered 0 to n-1. Rooms are connected by n conveyor belts. The ith conveyor belt connects I with I plus 1 mod n. If it is clockwise, the snake can go... Yeah, okay. Each snake wants to leave its room and come back later. A room is returnable. The snake can leave it and come back later. How many such rooms are returnable? Either all or none. Oh wait, off can be either. I see. Yeah, so... Well, if the out degree is 2, then none. Or like if it's 2 out only, then the answer is none. If there's a off adjacent, then the answer is 1. Otherwise, I guess if the in degree is 2, then the answer is none. The answer is yes, I guess, for this. And then the only other case is if there's a cycle. Alright, yeah, let's do this. see if you can go forward the whole way and backward the whole way. So if C is equal to this, then B cycle equals false. Else, if C is equal to that, then F cycle is false. So if F cycle or B cycle, then sys out and continue. Not many test cases, that's good. All right, otherwise, it's only if you can go, if you have 2 next to it. So char A equals line at I, B equals line at I plus 1 mod n. If A is equal to a period, or B is, then count plus plus. Three. Ooh. Oh, it's a dot hyphen, not a period. Three, 5, 3, 0. Looks good. Zookeeper is playing a game. In this game, Zookeeper must use bombs to bomb a string that consists of letters A and B. He can bomb a substring, which is either AB or BB. When he bombs such a substring, the substring gets deleted from the string, and the remaining parts of the string get concatenated. Okay. Yeah. What's the shortest string he can make? This sounds really easy. Just, oh, I guess, do you have parity issues or no? No, you don't. So every time you have an A, you match it with some B, doesn't matter, and then you delete B's after. Yeah, okay. Yeah, I think you can sort in Raif characters. That should be fine. There's no way that's gonna teely. So then int count 0 for char C in line. If C is an A, then count plus plus. Else if count equals 0, count plus plus. Else count minus minus. And this should be fine. Okay, what's going on here? Oh, it's got to be AB, order matters. I see. So then can we use a stack? Yeah, I think we can use a stack then. Okay, so for char C in stack, or in line. So if the C is equal to a B, if head is equal to -1, then stk plus head equals c. Otherwise, if it's not a head, then we can subtract it out. Tk, well then just head minus minus. We delete the b and whatever's before it. Otherwise, we have to add it. What? How do we subtract 1 twice from this? Oh, because I'm sorting it still. Yeah, good. Alright, that took way too long. That was a banger problem. Should have been like 1 minute, 2 minutes maybe. Yeah, okay, we got it at least. To improve the boomerang throwing of animals, Zookeeper set up an n by n grid with some targets. Each row contains at most 2 targets. The rows are numbered 1 to n, columns are numbered 1 to n. For each column, Zookeeper will throw a boomerang upwards, hits any target, it will bounce off, making a 90-degree turn. The boomerang can hit multiple targets and does not stop until it leaves the grid. Boomerang in column I hits AI targets before flying out of the grid. AI is greater than or equal to 3. Huh. Or less than or equal to 3. What? Got it. Are we only throwing them in columns? Okay. Oh, 90-degree turn to the right. I see. So it's 2, 3, 2, 1. Yeah, okay. So if it's 0, you leave the column empty. If it's 1, you put something at the top. If it's 2, if it's greater than or equal to 2, then you need a non-1 to the right. Otherwise, it's impossible. Yeah. And then if it's 1, you just put 1 thing in that column. Otherwise, you put 2. Yeah, okay. So it's not too bad. we can definitely do it. Okay, so now for int I equals n minus 1 greater than or equal to 0, n minus minus. If a at I is not equal to, well, if it's equal to 0, then continue. Otherwise, a at I equals, or if a at I is greater than 1, is this out impossible, -1, return, else break. So now we know the rightmost thing is a 1. So that's fine. Okay, so now int, what do we print? The number of things, okay. Presume 10 to the 5th, so print writer. Man, I can't type today. Alright, so that is printing our answer. Now we just have to get the answer. So for int I equals 0, less than n, I plus plus. We should also have a boolean use 2, which is initially false. Okay, so now if a at I is equal to 0, we should probably also have, well, this is just the x. Alright, so now if it's equal to 0, then continue. Otherwise, we need to place at least one thing here. So if use 2, yeah, we'll start this at 1, add 1 here. Then x is dot add x, y is dot add y plus plus, x is dot add y, or x, y is dot add y. And then continue. Oh, then we need to worry about use 2. Otherwise, x is dot add x, y is dot add y. Okay, so now if a at x is equal to 1, then y plus plus. Use 2 equals false, else if a at x is equal to 2, then use 2 equals true, else use 2 equals true as well. All right, let's try this out. One one, 3 1, 3 2, 5 2, 5 3, 6 4. So that'll give us 3 0 3 0 2 1. This should be 2. Use 2 equals false. 5, so we just removed 3, 2. Yeah, I think that's fine. It's good to test. Now, why is this impossible? Oh. You can't have 3 in any row or any column. I missed that part. All right, so I see. So what does that mean? If you have can you never have 2 2s in a row? Yeah, you can't ever have 2 2s in a row. If we don't have 2 2s in a row, we increment in most of these places. It's taking me way too long because this is probably has a bunch of solves. Not as many as I would have thought. Huh, it's really hard. Shouldn't be that hard. I guess we should read E then. Nice job, Eric Toe, first place. Like to see that. Carrots for rabbits. There's some rabbits in Singapore Zoo. To feed them, zookeeper bought N carrots with some lengths. However, rabbits are very fertile and multiply very quickly. Zookeeper now has K rabbits and does not have enough carrots to feed all of them. To solve this problem, zookeeper decided to cut carrots into K pieces. So use K rabbits, 1 piece per rabbit. All the resulting lengths must be positive integers. Big carrots are difficult for rabbits to handle and eat, so the time needed to eat a carrot of size x is x squared. This seems like a super classic problem. Seems like if you've seen this before. Can we binary search the length of the smallest cut? Yeah, first we can binary search the length of the smallest cut, and then we can binary search how many. Because they're all going to be 2s and 1s. Is that true? Maybe that's not true. What if you have something of like 10 size like 7 or something? If you have 10, you have 7, then you get 4 pieces. You can get 5 squared plus 5 squared plus 3 squared plus 4 squared. One second, time limit's tight. Huh, do we want to distribute these mostly equally? Want to distribute. It's hard to tell. We could binary search that. If you're really good, it takes you like 6 to 10 minutes to get this. 6 to 11 minutes. All right, D has a bunch of resolves as well. Let's go back to D for a minute. Yeah, I know how to do D, I just don't want to get it wrong. That's the only thing. So you can, like, if you have a 2 followed by oh, it can't be followed by 2. It also can't be followed by 3. So 2's have to match to a 1 that's to the right. Okay, and then a 3. Well, you can match a 3 with a 2 with no problem. Or with a 1. Well, 3 can go to anything, yeah. So each 2 needs to match with a 1 to the right. So they match this 2 with this 1. Yeah, okay. Can't match all 2's with a 1 to the right. All right, yeah, we can do this. So this is going to be D2. The last thing isn't a 1, and it's impossible. Okay, we also need a match with stack. Okay. So let's worry about this first. So what else do we need? So 3's and 2's need a match. 1's are fine. And we'll also need an array deck integer stack is new array deck. Okay, so if a at I equals 1, if it's equal to 1, then stk at a of I, well, I don't need to add to the stack. So okay, so if 3 match int is equal to n, then 3 match int is equal to I. Wait, can a 2 match with a 3? A 2 can match with a 3. Yeah. just not an immediate 2. And two things can't match with the same other thing, though. Yeah, okay. All right, so we've got a stack. All right, so let's just write this out. So a 2 can match with a 1 or with a 3, but not a 2. A 1 doesn't need a match. And then a 3 can match with a 1 or 2 or 3. Okay, so these will be 2s and then non-2s. Okay, so we don't need this 3 match index now. It's equal to 1, non-2s dot add I. If it's equal to a 2, then if non-2s dot is empty, this out -1 and return. Otherwise, match with at I equals non-2s dot remove. And then 2s dot add I, because if 3 could match with us, then it would be fine. All right. Then, finally, we want, if it's a 3, non-2s dot add I. If non-2s dot is empty, or if 2s is empty, if it's not empty, then match with that I equals 2s dot remove. And else if non-2s dot is empty, it's not empty, that means we can match with a 1 or a 3. Otherwise, we have no one to match with, so then we can just print -1 and return. All right, so this is great and all, but I think this is just more harm than good. So we'll comment that out. This part's still code I don't want to type a second time. Okay, so we also want the y, which will be n initially. Y's dot add y minus minus. Can't share with this. X's dot add x, or I. X's dot add from I. Y's dot add y. X's dot add mesh with at I. Y's dot add these need to be the same y. Yeah, you can't match a 2 with a 3. Yeah, 2 can only match with a 1. So if you match a 2 with a 3, you have an issue. All right. Okay, ones add this. Non-ones. Be non-ones. Okay, so the 2 Yeah, okay. All right, so we match with the y. Non-ones add I. Because you can match with this x if you want in the future. Y's dot add match y. Well, this should be, okay, that should be matched with an I, but same y for this thing here. Good, okay. Then you can match with us later if you want, okay? And then how do 3's work? So if non-ones is empty, yeah, match with it. And then, oh, we also need y minus minus here. Okay. Then, yeah, we don't need to worry about the y. We can just say y minus minus here. But yeah. Okay. So now we just need the same thing here. Except these are both at y. All right, that took way too long, but we're fine. 7 things. Let's try it. This should be impossible. Oh, it's because I'm running the wrong code. There we go. -1. $10, huh? 10 seems like a lot. 10 seems like maybe way too many. Let's try it though. So 1, 2, 3, 4, 5, 6. So first we put 1 at 6, 6. Then we put 1 at 5, 5. Then we put 1 at 4, 4. And at 6, 4. That's right. Then we put 1 at 3, 3. Oh, wait, what? If it's 0, yeah, okay. A at I equals 0, continue. Three, 4. Six, 4, I imagine. Okay. Then we have 6, 6. Then 1, 6. And 5, 6. Wait, what? Nope, not right. Oh, we don't need to add this. Yeah, okay. Ugh. Okay. Am I print writing correctly? I am. No extra debug. That's fine.
Problem debug, wrong answer, test 1, sir.
Wrong answer, test 1? For which column? Sure does. I don't know what game you're playing. 6, 6. 5, 5. 3, 4. 6, 4. 1, 6. 2, 0. Oh. Wait, what? Hang on. I may have actually gotten this wrong. Why am I getting this wrong? 3, 4, 6, 4. So I'm matching this one twice? Never matching 5? Oh. 1's 1. Thank you. That was, man, that's very nice. That was in pretests, pretest 1 even. Okay, 6, 6, 5, 5, 3, 4.
I don't understand how to change the volume.
6, 4. And then 1, 5. There we go. Okay, good. Problem, man. No, I didn't. I got it right. That's a lie. I'm telling you, this is right. Codeforces. 6, 6, 5, 5, 3, 4, 6, 4, 1, 5. Two, 0, 3, 0, 1, 1. Am I misunderstanding something? Like, my solution is equivalent to this, isn't it? Do we have to print the output in a certain order? Is my output format wrong? My output format's fine. I'm printing like the same thing as this, just like lower a little bit. Right? Six, 1, 2, 3, 4, 5, 6. 6, 6, 5, 5, 3, 4, 6, 4. Wait, 1, 6. I printed the wrong code. Man, I submitted the wrong code again. I've submitted exactly the same code before, have I? Did it not get the right answer? Oh, I was probably just looking at the wrong thing. 6, 6, 5, 5, 3, 4, 6, 4, and 1, 5. It's 2, 0, 3, 0, 1, 1. What? Clarification request, maybe? How 200 people are getting it, though? I'm gonna ask clarification because I don't get it. I've drawn out all the paths. It looks right to me. Just hasn't tried it. All right, well, let's move on. There's some rabbits in the zoo. Zookeeper bought end carrots with these lengths. Yeah, okay. So if we knew like the value of a carrot, we could know how many to distribute to each position. And then once we've done that, we need to distribute the rest of the carrots in a smart way. So like we need I don't want to say their checker's broken. Oh my god. Okay, so I'm just... It's very nice of them to answer that. That's incredibly generous of them. So I'm just silly. Yeah, that's fine. Alright. Yeah, I'm just stupid. That's fine. Good problem. I'm just an idiot. Can't read. That's fine. Anyway. But end carrots with these lengths. Yeah. Okay, alright. Let's move on from that. Does this have a lot of wrong submissions is my question.
I'm not sure how long to set it for.
It does. Oh, we'll just do this k times. Yeah, we don't need to do any binary search. So just k times, we will find the thing that would benefit the most. So now we just need what's the cost in order 1, which I think we can do. Yeah, okay. All right, good. So in parts, and then the length. Yes, this is going to be a long, right? And this will also probably be a long. So the cost will be some stuff. Benefit of 1. Okay, long O cost will be the cost. Parts plus plus, long N cost is the cost. That's minus minus. Return O cost minus N cost. Seg's length will be this. Parts will be 1. Seg's length will be this. Okay. And then point I equals 0 less than k plus plus. And type equals this. Or we don't. What am I doing? Priority to. Nope. Seg give 2 equals pq dot remove. Give 2 dot parts plus plus. And then pq dot add give 2. Okay, then long total equals 0. Print the total. Or do we print? Yeah, minimum sum. Alright. So then for seg s in pq, well, we just say well, not pq dot is empty. Total plus equals pq dot remove dot cost. So now it's this cost function we need to figure out. How do we do this? So if you've got n things, n over k is the smaller. Yeah, okay. So int smaller size will be the length over parts. Int n smaller will be, well, I guess n bigger is easier, equals the length mod parts. Int n smaller will be parts minus n bigger. So smaller cost will be long smaller size squared. We also have a bigger cost. this will be smaller size plus 1, that's the bigger size. Times that, and then return smaller cost times smaller size plus bigger cost times bigger size. Or times n bigger. Yeah, good. We'll listen for a verdict, but I think it's right. Zookeeper is buying. I see. Zookeeper is buying a carton of fruit to feed his pet wabbit. The fruits are apples and oranges, which are represented by some binary string of length n. 1 is an apple, 0 is an orange. He's allergic to oranges. He'd like to find the longest continuous sequence of apples. All right, but there's a catch. Which is we try it for all LR pairs. Yeah, okay, so try all substrings and find the longest contiguous sequence of apples. Data structures problem, I like it. Or data structures sweepy array problem. Got it. So longest continuous sequence of ones. So let's consider each block of one separately, maybe. If we have some block, you've got the n choose 2 part, like within. That's easy enough. Other than that, we need to know when to the left is it beaten? When in this direction do we get a better one? So we can do that with the sweep beforehand. Yeah, okay. Do 2 sweeps. So the idea is we're going to do sweep from left. And also sweep from the right. Oh, this doesn't handle ties super well. Yeah, I'm not counting either of them for ties. So maybe we'll count the left of them for ties. All right, so then for the stuff to your left, you want to find first left bigger than you. First left bigger than or equal to you. And then you also need the first right strictly bigger than you. And then you can choose any of those endpoints. And the left and the right, because they're independent. Yeah, okay, easy enough. We should, hope we can do that in 20 minutes. That'd be nice to be able to do in 20 minutes. How many solves does it have? F? Okay, so we're not going to do super well this round, but that's fine. Okay, so we'll do the sweeps. So there's like the left tail, okay. I understand what that means for me. And then we probably also want a stack. Yeah. It'd be nice if it always starts and ends with a 0, but it doesn't, so that's fine. Okay, so we'll just handle that separately. So if line at I is equal to a 0, we'll do one thing, otherwise do something else. The one case might be easier. Let's handle that first. In this case, L tail at I equals 0, 1, otherwise L tail at I minus 1 plus 1. We also need to fill in beaten on L. Okay, so well, stk not stk dot is empty. And stk dot peak well, this thing is less than first left less than or equal to you is less than me. Is less than L tail at I. Then L tail or stk dot remove last. Okay, so pop from the stack as long as I need to. It's empty, -1, otherwise stk at, or stk dot peak last. We'll just call it beaten on L. Yeah, okay. Alright, so now if it's a 0, then L tail at I equals 0. If I is not equal to -1, or it's not equal to 0, then stk dot add last I minus 1. Are there any other cases? I think that's fine. So now we've built the stack one way. Yeah, now we have to build it the other way. Okay, so we need basically the same thing over here. This is the right tail. We'll keep the stack. And then we need beaten on R. I equals n minus 1. Greater than or equal to 0, minus minus. So 1, if I equals n minus 1, print 1, this should be R tail, should also be R tail at I plus 1, okay? And R tail, peak last, is less than or equal to R tail at I, remove the last, beaten on R, equals this, otherwise this, okay, R tail at I equals 0. Yeah, and line at I plus 1 is equal to this, stacked at add last, I plus 1. I think that's fine. So now we have where we're beaten for each L and for each R. Oh, okay, also we need to process this end here. Yeah, so no, we don't worry about what's in the stack. Because that's all this does. All right, I think we're fine. I think we're fine with that. So now we need to process each continuous block of 1s. Shouldn't be too bad. Do we have to print the answer under mod? No, I guess not. Because it's n cubed at max. All right. So let's make this a long. All right. So now we need some stuff. Okay, so everything's smaller than us. We can handle that. Be an int now. In this case, ans plus equals I times range size minus I plus 1. So all of those small ranges we can take care of. Runtime should still be fine. Now, we also need to handle the extra cases. Okay, so int L end equals beaten on L at, ooh, okay, so int range start equals start at, int range end equals start at minus 1. Okay, so beaten on L at the range end. And then int R end will be beaten on R at the range end. Okay, that's fine. Or range start. Good. Okay, so then we need to do some math here. So long L size, if Ln is equal to -1, then L size will be range start. Less than. Range start plus 1. Otherwise, the left size is limited. Okay, so then well, let's just do okay, otherwise, first legal start will be L end. That's the index that beats me, minus the range size. Plus 1, I think. Because if you subtract out the entire range size, or is it plus 2 even? So let's say I am 3 big, then this one is the index that beats me. It's plus 2. Okay. Yeah. Okay. This isn't a long, well, we can make it a, yeah, let's make it an int. Now, int last legal end. We'll do the same thing one more time. How's your time looking? We're fine. Last legal end will be n minus 1. Okay, otherwise, last legal end will be r end plus range size minus 1. Oh, wait a minute. Darn it. Darn it. I have to do this for each prefix and each suffix too. Oof. Darn. Okay, it's just harder than I thought. We can still get it, but it's annoying. Okay, well, ants plus equals range start minus first legal start plus 1 times long range end last legal end minus range end plus 1 times range size. Yeah, this is wrong though. It's going to be too small. It's also just crashes. Yeah, the prefix and suffixes is what's killing me. Because it's this and this, so I'm wrong there. Okay. This is the whole thing. Okay, so now we also need this is annoying. So 2 more cases, and I have to handle both of them. I hope there's a cleaner way of handling this because this is just a mess, to be honest. All right, so now we can do this. For int pre-length equals 1, pre-length is less than range size, pre-length plus plus. We need to know when each prefix gets beaten. Yeah, okay, we can still use this stuff though. These might be interchangeable, I guess, but let's just copy and paste. What could go wrong, right? When you copy and paste. Okay. So for each of these prefixes, what are L end and R end? Oh yeah. So the left end is interesting, the right end is not. 7:33 a.m. Thank you for telling me that, Zero. This is just gonna be range start plus the pre-lang. Well, we don't even need to worry about this. This is just going to be 1. Yeah. This isn't range end. This is range start plus I, or plus pre-lang minus 1. Yeah, so when is it beaten to the left? Then we get our first legal end, or first legal start point. Yeah, and that times range size times prefix lang. Okay, this shouldn't be, this should be pre-lang as well. Okay. Now let's handle all suffixes. Suff length, or let's just, yeah. Let's delete this and make basically the same changes to this code here. Okay, left endpoint is now not important. This is now 1. Okay. Oh wait, is that a bug? Yeah, it should be R end. Okay, thank goodness for copy and pasting. R end is equal to -1. Wait, what did I do? our end is equal to -1. Last legal end equals n minus 1. Okay. We don't want range size, we want suffix length. Oh, this is just 1. This is suffix lang. This is our end plus the suffix length minus 1. It's the last legal endpoint. The range endpoint is when we're beaten at R. This isn't the range start. This is range end minus suffix length plus 1. Yeah, okay, I think that's fine. Lots of stuff going on. A little bit longer than 20 minutes. And now we're over counting. Why is that? Oh, because we count this part twice now? Yeah, it's kind of hacky, but I think that's fine. Does it work with 2 ranges? It does not. Or maybe that's the fact that we start with a 1. What part of the code is this? Here. -5. I hope not. -5? What the heck? So unbeaten to the left, unbeaten to the left, unbeaten to the left. This is beaten at index 1, 2, or at index 1. Unbeaten, unbeaten to the left. It's tied here, so 3. Okay, yeah. All right, from the right, it's never beaten. This doesn't matter. This is beaten here. No, it's never beaten. That's never beaten. That's never beaten. Okay, that's fine. Yeah. All right, so all right, and now way I'm counting this is messy, but we can handle it. Okay, so initially it's 0. After adding all internal substrings, it's 2. Yeah, that's fine. Okay. That makes things easier to read. Okay, so prefix length what's this flow range included? So we've got 1 on the left, 1, 2, 3, 4, 5, 6. So it should be 12, so that's fine. Prefix of length 1. Full range added -6. That's the problem right there. So the full range can be negative. Range start minus the first legal start. So this range is just this last thing. So the range start is position 6. The first legal start is position 4. Yeah, that's fine. The last legal end this should be our end. I thought I could have sworn I changed that. Okay. 30. Let's make sure this is still 12. It is. Let's make sure this is 156. It is. Find and replace all. Some people ask about that sometimes, but we don't want to debug that. Okay. One, two, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I think that's fine. Find my multiplications. Uh-oh. Good thing we check. Yeah. Not great, not great. All right, so definitely go for G1, and that's it. Unless G2 is like basically as easy. This is an easy version of the problem. The only difference is that Q equals 1. You can make hacks only if all versions of this problem are solved. Zookeeper has been teaching Q sheep how to write and add the ith sheep has to write exactly k non-negative integers. The ith sheep has to write this non-negative integers with this sum. Okay. So you have to write a bunch of integers that sum to some number. Okay, strangely, sheep have superstitions about digits, and believe 3, 6, and 9 are lucky. To them, the fortune, we're in base 10, presumably. Okay, yeah, I think we're in base 10. To them, the fortune of a number depends on the decimal representation of the number. The fortune of the number is equal to the sum of the fortune of all digits. And the fortune of a digit depends on its value and its position. It can be described as follows. Okay, so I think digits that aren't 3, 6, and 9 don't matter. Okay, I see. So you've got so you've got several digits. Three, 6, and 9. And it's like you get multiples of them, blah, blah, blah. Okay, he wants to maximize his fortune among its k written integers. Can you help them? Single integer k. The number of numbers each sheep has to write. All right, you have to write k numbers. They need to sum to n. Got it. K numbers sum to n. Then you need to maximize this thing. So there are a logarithmic number of different things, I think. Yeah, wait. Okay. So there are 5 of these. So the total number of different values that actually give you anything is 5 times 3. Well, it's literally just this entire table. Yeah. So there are 15 values that are important. Let's get some new paper. Well, I got this here. 15 important values. And then you need to pick some numbers that sum to m. So it's like knapsack sort of thing. Oh, it's like modified knapsack. So each yeah, it's like tricky knapsack. I guess let's get what are exactly these constraints, because these are kind of important. The fact that there are only 3 of these might make it abusable. It's also kind of like 0k knapsack. So you have H is interesting, but it's too hard, I think. just from the point value in the scoreboard. I don't think it's worth my time to think about. Yeah, no solves, and well, okay, Tourist isn't doing the round, but like Andrew, he hasn't gotten it. Some people might be smart in going for it. Man, I'm still going up? That's kind of insane. Because I'm not doing too well, that's for sure. Huh. I didn't think D through F were really that bad. I guess F can be annoying, but D and E were basically like, what are you doing, Anderson? My boy. Daniel, oh my god, team, come on. UCF is just choking today. There you go. Like to see that. Good job, John. Solid, solid. Not bad. Same thing with Josh. Is Josh gonna earn red today? I should go back to competing since this is rated for me. He needs about 200, so not unless he gets F. Okay, anyway, back to G. 15 important values. We need to pick some things that sum to N. Yeah. And then we get K groups. Can these numbers be 0? Non-negative, which means they can be 0, because 0 is not less than 0. Okay, so we like have at most, do we have to print what these numbers are, extract the answer? Maximum total score, haha, thank you. I appreciate it. So we have at most K dollar, we have at most N dollars. Yeah, we have N dollars. We don't have to spend all of it because we can just pad with ones. Or we do have to spend all of it. Yeah, okay, so that's tricky. But you don't have to use all of your numbers. So you get like at most K groups that sum to N. But it's tricky because N, like you might have issues with that. Might not matter. Okay, so we get at most K groups that sum to N. We can pick, N is not super big, right? What's our time limit? 3 seconds? It's pretty normal. Okay, so yeah, what's the idea here? We can pick 0, 1, or 2, or 3. Of a digit. As a multiple of 3. Or we can like toss that digit, I guess. Yeah, okay. So we can pick 0, 1, 2, or 0, 1, 2, 3 of this digit, or we can get as many of the digits we want, I see, for free. And then, what else? The sum of our numbers has to be some given value. You can pick up to k groups. How big is k? K can be big. I think I can do n log squared. So what is log here? Log is 20. So this is going to be 10 to the 6th times 400, which is 4 times 10 to the 8, which is uncomfortably large, but they're quick operations. Might pass. 36 minutes, I guess we'll give it a shot. So, yeah, what's the idea? We want to do some shenanigans. They kind of look like this. If we know how many yeah, okay. So we'll look at each digit like independently. Can we even do that though? Maybe. Let's worry about that in a minute. Okay, so now we've got like a DP where we want the sum, and we can pick at most k, yeah. And then you can take 0, 1, or 2, or 3. So we can make this a 0, 1 DP by increasing the number of things by log n. Yeah, okay. So make 0, 1 DP, okay. So the sum stays the same. Sum stays the same. But now you can take 0 or 1 like chunks of these things. Man, we're really transforming the problem quite a bit here. It's hard to wrap my head around all of it at once. Okay, so now we've got chunks of like log n things. And each chunk you can take 0, 1, 2, or 3 times. Yeah, so we'll do a bunch of sweeps through the array. Okay. I think we can do this. And then we do this for each digit. Yeah, okay. All right. Sorry, I need more screen space here, guys. These are like the equivalent difficulty. If I don't know how you would solve it otherwise. Yeah, this is gonna be, if I have time to get one of them, I'll have time to get the other one too. Okay, so how is this gonna work? Okay, so now static int array, bonus, I guess this can be private. Size 6. Okay. Alright, so what is n? Oh, this is not k. Okay, so this is the digit cost. There's also the bonus. Make that a long. And then we've got some array. This will be a long array, I guess. Best sum. Okay. Alright, so this will, what's this gonna do? Update best sum, maybe? Yeah, update best sum array. Like after taking this digit in at most k places, each at most 3 times. Okay. So for int digit equals 0, digit is less than 6, digit plus plus. Long bonus will be bonus for digit. Digit cost is 1. Digit cost times equals 10. Yes, you can do this. Isn't this wild? Pretty cool though. Bonus for digit at digit. Alright, long array. Best for n equals new long array. This arrays that fill best for n. Let's say static long infinity equals long 1e18. infinity. And then parent writer out equals to parent writer system dot out. In this case, out dot print line. Best for n at this. Okay. So in this case, we want to fill which digit? Oh man, this has a ×5 in it too, doesn't it? Might have TLEs. Are people TLEing on this? Not really. Oh my goodness. And we're running out of time. Okay. Well, let's try it. So the digit cost will be digit cost times 3. The bonus will be bonus for, well, it'll just be bonus. The best sum will be best for n. Yeah, okay. All right. Does G2 have a bigger time limit? No. All right, so best sum in cost in value. I guess the value should be a long. Well, it's really 0, 3 knapsack, right? I take it 1, 2, or 3 times. Called n times log n times. Oh wait, n times log k times 5, which is sick. So we're actually set here. Yeah, okay. So this should be fast enough actually. Okay, so we're going to overwrite from things before us in the DP, which means we want to go from right to left. No, we're going to read from the things after us, things with more money. Yeah, no, we want to read from the stuff before us, because that way we can just answer all the queries. Cur sum equals, so we read from the things before us, which means we want to go from right to left. Cur money is greater than or equal to 0, cur money minus minus. Okay, if best, well, if line set 2 equals best sum at current money, if current money is greater than cost, set 2 equals math.max occasionally is like a constant factor slower than it needs to be, so that's why I'm just writing my own. the max of set 2, best sum at current money minus cost, greater than or equal to cost, plus value. I won't worry about constant time optimizations yet. This plus value minus cost. Say I won't worry about constant time optimizations, then I'm doing constant time optimizations. Okay, you take 0, 0, 3 knapsack, okay. Yeah. Okay, so now this is the split it up into log things. All right, so now we need to split this up into groups. I go 0. Okay, 4. Yeah, I equals 0, I is less than cost at size, I plus plus. Run this 0, 3 knapsack. On best sum, the cost will be cost dot get I, the value will be values dot get I. Okay, so now we just need to figure this out. So how do we split this up into parts? So int highest bit equals integer dot highest bit k. Oh no. Okay. Scared me for a minute. Okay, so k minus equals highest bit. So now 4 int I equals 0. I is less than 22, I plus plus. If k and 1 left shift I is not equal to 0, then we want to do some stuff here. So in this case, yeah, include it. So the digit cost is already multiplied by 3. Okay, so in this case, we say cost.add. The cost will be the digit cost, left shift by I. And the value values will be best sum, nope, will be bonus, left shifted by I. We take 0, 1, 2, or 3 of those. Okay, so now 4 int I is less than integer dot n trailing zeros of the highest 1 bit, I plus plus, less than or equal to this, actually, is what I want. Cost dot add digit cost left shift I, bonus left shift I, do this. Okay. Man, that was way easier to type than I would have thought. 18 minutes to debug. I think we can do it. Nope, just kidding. Yeah, the reason for that is because best for n at 0 should be 0. Oh, no. No. 63. All right, I have to go to the bathroom. I'll be right back. All right, 15 minutes left, huh? 15 minutes left. Um, wait, I'm too high. I should be too small. So I think one issue, at least, is that I'm not accounting for zeros. Like, yeah, if Why is this too big? So 30 would be 2 plus 19 plus 1 times 3. So 2 plus 3 plus 3 is 8. Am I just doing... Oh, this should be minus. Yeah. So this should be this, and now I also need costs dot add digit cost at 0, or digit cost and cost dot add bonus. Okay, so now I should either work or be too low. I'm too low, which is fine, because I also need, I can also take anything else. So I can also take any of these things for free. Oh, no, I don't compile. This shouldn't be a base cost. Should be an int. Let's not pass it in. This is going to be 3 times the digit cost. So this is going to be costs that get I divided by 3. I think this is fine. Oh my goodness, it works. It works, it works, it works. Okay, so this we don't want. We also don't want this. Bonus for digit. These are all small enough. Yeah, it's turned into a long. Pretest 3. Are we going to TLE? What do we do if we TLE? Switch to C++. Runtime error. Runtime error. All right, we can fix this. What could possibly runtime error? Surely it's an array index out of bounds exception, right? Runtime error. Oh. What if k is 0? Can k be 0? K can't be 0. Can things be big? Runtime error, highest 1 bit, that should be fine. Into the 6, and the 6, that's fine. Digit cost, oh. This is an issue. This needs to be a long. if costs that get I less than 26. Just 27, I guess we can do. Doesn't matter.
Problem G, wind up time limit exceeded test user.
No. No.
Problem G, tuned up time limit exceeded test user.
Ah, it's so close. Maybe this part I can speed up? What if we don't do this? That doesn't work. Would this pass in C++? Probably. Or maybe not. So close. So close. I think I'm out of time here though. Anything silly I can do to speed it up? I could just run it. Yeah, okay, that's it. All right, unfortunate. How'd I do? 135th plus 50. Not the end of the world. How'd my friends do? Raidwish got it. Nice job, sir. Well deserved. Only solve on H. Good job. Yeah. Okay. So I don't think these two are that difficult, or that different in difficulty. But I don't know. Maybe I'm wrong. Yeah. Although, I guess maybe not. There were some people who got the first but not the second. I'm not really sure. Okay. Other friends. Josh went up. Good to see. Good to see this. Is this a new yellow here? 205 plus 97. It looks like it. Yeah. Yeah, and a bunch of people who just like kind of choked. That's fine. Man, and then I choked as well. Couldn't get G. How did, Ooh, 3 hacks. Hang on. Hold on a minute. Problem B gets hacked. Is mine gonna get hacked? I think I'm safe. Let's look at pretests. What are pretests even? Are they hard? I guess we can't see them. Can't see the submission either. Oh, and then he didn't get it afterwards. That's kind of sad. Interesting. Alright, well, nice job, Colin. You beat me on hacks. I don't really play that game, but maybe I should. I guess I should notice when other people are playing it. These are everything that's hacked. Let me... I wonder if I'll fail system tests for B again. It's kind of a common theme here. Well, anyway, time for solutions. So I'll give solutions to everything I know how to do. Maybe not everything there is, but yeah, should be fine. Okay, let's start with the easy problems and we'll move up from there. And then I won't do age because I don't know age. All right, so problem A, box is pull. So the idea behind this problem is you have a box at some position and you would like it to be in some other position. So what you can do is you can stand like over here and then you can walk one direction here, and after that the box will move over here and then you'll be here. So the idea is, if you look at the box, it's going to have to maybe change its x-coordinate, so maybe its x-coordinate has to move like this. It also might need to change its y-coordinate, so you look like this. And those two numbers are both relevant, so we'll keep track of both of them. But what we can do is just pull it all the way by its x-coordinate, then pull it all the way by its y. There's no reason to switch. In that case, we have to switch one time. So when the box is here, we'll be standing over here. And we have to move up and then left. So we have these 2 extra wasted moves. So we always have to pay those moves, except in the case where we don't. And the time when we don't is if you move only in one direction. So if the x's are the same or the y's are the same. In code, that winds up being really simple. It's just, you read in the 4 variables. If either the x's are the same or the y's are the same, then you don't have to pay that extra cost. So it's just the Manhattan distance. Otherwise, you have to pay the cost of 2, because you have to switch sometime, so it's Manhattan distance plus 2. And that's problem A. Awesome. All right, problem B. Belted rooms. In a snake exhibition, there are n rooms, 0 to n minus 1. With each snake in a room, the rooms are connected by n conveyor belts, and the ith conveyor belt connects some rooms. Yeah. So you've got basically this circle, and the way it works is there are a couple ways of going around the circle. You can, like, maybe you can go like this. You've got some single-directed edges, some multi-directed edges like this maybe. So in this example, what can happen is every snake can leave where they are, and they can go in a circle, basically. And that's, yeah, so every snake can follow the circle and get back to where they started. Yeah. And you want to know for each position, I'm just like hesitating here because I want to make sure that everything I say is actually true and I'm not about to get hacked here, but I think I'm fine. For each position you want to know, can you leave this position and then come back to it eventually? So obviously if you have a multi-directional edge next to it, you definitely can. You can leave that position and then you can come right back along the same edge. So that's always possible. But if you don't have one of those edges, it's still possible sometimes, and that is if you do this full loop. So the loop is possible if you don't have, either you don't have any like backward symbols or you don't have any forward symbols. So if you can go backwards through the entire array, then you don't have any forward symbols, which means then it's possible, and same thing, inverted. So I think, I mean, people are getting hacked, so I could be wrong, but I think it looks like this. So either you check if there's a forward cycle or a backward cycle, and it's a forward cycle if there are no greater than symbols, or it's a backward cycle in that case. If there are no less than symbols, it's a forward cycle. And if either of those are the case, then all n nodes can be reachable. Otherwise, any node that's adjacent to a hyphen is reachable. So you just count how many of those there are and print that. I think that's it, but I'm not totally sure. So we'll see in system tests, which might happen at the time I'm doing this review. All right, problem C. So yeah, so in this problem, you've got some string initially full of A's and B's. Here's a good example. And every time you have two adjacent B's, you can delete them. Also, anytime you have an A followed by a B, you can delete both of them. And now the question is, if you want to delete the maximum number of things, how many things can you delete? So in this case, what might happen is you can delete this A and B. Afterwards, the string will look like this. And then you can delete this A and B. And now you have just B and A. You can't do anything from there. So I guess the thing to keep in mind here is like the constraint is stuff that's earlier kind of has less freedom. So if you have the last thing in the array, if it's an A, well, an A can't ever get deleted by something to the left of it, so we won't worry about the A. But if it's a B and it's at the end of the array, it has more freedom. It can delete a B or an A in front of it, which means if we make decisions based on what's on the end of the array, we might make the wrong decision, and we want to avoid doing that, so we'll use like a greedy, but do it when we have less freedom. That way anything we decide can't be beaten, basically. So how exactly do you handle that? Well, we're going to go left to right, and then every time we see a B, if there's anything in front of it, then we'll delete both of them. We know that's helpful because this B can only delete things that are in front of it. So if there's something in front of it, if that thing's a B, that means this is empty, right? If the thing in front of it's a B, that means that B can't be used for anything. We would have deleted it otherwise. But if it's an A, that means we might as well use it to delete the A, because that way we're not wasting one of our free deletes. So that's the idea. And I'm pretty sure that's optimal. So yeah, we'll just keep track of I call it a stack. It's just an array of characters that we've seen before us. And then for each character, if it's a B, then if the stack is empty, we just have to add it, because there's nothing to delete. So we'll just put it on the top of the stack. Otherwise, we'll delete the top thing from the stack. And if the stack isn't empty, then we will, or if it's not a B, sorry, if it's not a B, then it's an A, so we just put it on top of the stack. And at the end, we just print the size of the stack. That's it. You might be able to implement this cleaner if you use like an actual stack rather than build your own like I did with these two variables, but that's fine. I don't think it's too difficult to understand. Okay, awesome. That's C. Very easy. A very easy problem. Shouldn't be an issue for anyone. Problem D was also not too bad. I kind of choked on it, but yeah, not the end of the world. So the idea for problem D was you have a bunch of these animals, I guess, and for some reason you decide that you're going to harass these animals by throwing a boomerang at them. You're going to throw a boomerang up, and the boomerang will bounce some number of times. Every time it hits some animal, it'll turn to the right and keep going. Now, they have this very convenient constraint, which is the boomerang bounces at most 3 times. So the worst thing that can happen is it'll bounce up, then it'll bounce to the right off some other x, then it'll bounce down, and it'll bounce left. But it's only going to bounce those 3 times, so it's very easy, which means there are only 3 cases. Either it bounces once, bounces twice, or bounces 3 times. Let's look at each of these separately, and then we can get our solution from there pretty easily. So if it just bounces once, the idea is that we'll have some animal here, and then we'll have nothing else, nothing else below it in the column, and then we'll have nothing to the left of it. But we might have stuff up here. This stuff doesn't matter. So that's kind of the case for 1. We've got the animal, we've got nothing below it, and then we have nothing to its left. For 2, we'll have an animal here. We don't know about what's above it. That's not really important. We need to have nothing below this animal, wherever we put it. Then somewhere later on to the right, we'll have some other animal, right here. And then we'll have nothing below this animal, like that. So here we'll have like an X here. We'll have nothing below it. Then we'll have an X over here. We'll have nothing in here. And something like that. Now what you'll notice is this second thing right here, when we throw a boomerang up from this position, we're gonna hit this. So this, obviously, it can't be a 0. I guess 0 is this other case, right? We'll draw it as 0, just like kind of as a token. I'm not covering, this might be in my face. There you go. So, yeah, the 0 is just kind of empty. Now, like, you can't match the second part of a 2 with a 0 because there needs to be something there. For the 0, there can't be. But I guess also there's the additional constraint, which I forgot to mention when describing the problem, which is you can't have 3 things in the same row. So you can't have 2 2s in a row. Or you can't match a 2 with the start of another 2. Since this has to be empty, that means this thing here, it actually has to be a 1. So if this is a 2, this needs to be a 1 following it. I guess, so yeah, that's it. That's the important part. And I guess you might ask, why is it not a 3? Well, we'll see why it's not a 3 in a second, but that's not the end of the world. The final case is a 3. So if this is a 3, what's going to happen is we're going to travel along this path here. Let's use blue. We see this position, so we'll go to the right. Then we need to hit something else. We'll see it, so we need to start going down, and then we need to hit some other thing here. And then we'll start going to the left. So if this is a 3, we actually can make this whatever we want. Because it can be a 1, in which case it'll be this, and this will be empty. It can be a 2, we can put something else here and make these all empty. Or it can be a 3, we can put something here, we can go like this, we can have another thing, we can make these all empty. So a 3 is compatible with anything. What a 3 looks like is this. It's got an X here, an X here. This is empty, this is empty, this needs to be empty, this needs to be empty. Because you can only have 2 things in a column, this also needs to be empty, and then this needs to be empty as well. So you have something like that. So that's the constraint. So first, what we're going to do is figure out how to match things. So the 2 is the very nitpicky one. The 2 can only match with 1s. So we're going to go from the right to the left, and anytime we see a 2, we're going to match it with a 1 if we can. The 3 can match with a 2, well, it can match with a 3, or it can match with a 2, or it can match with a 1. The matching with a 3 and the 2 are fine, because no one else cares about them. But the 1 is an issue, because if you match with a 1, you might be taking up spots for a 2 later on. So you don't want to do that unless you have to. That's the idea. And then once we have where everyone's matching, it's pretty easy to implement. We just have to get the y-coordinates right. All right, so how does this actually work? So this part is not even necessary. The idea is we're going to do a sweep from, oh, this is not my right, so this is my old solution. I misread the problem. Yeah, this part's not necessary. We're going to do a sweep from right to left, and we're going to keep a queue of all of the open positions that are 1s and that aren't 1s. The ones that are 1s will be prioritized to 2s, and the non-1s will be for 3s. So if it's a 1, then we add it. We also clear out this y so we can bounce to the left, and we don't want the next y hitting us. And we keep track of, in our queue, we put, all right, this x coordinate is something you can bounce off of, and then this y, this is like the y coordinate of the 1. So when we pop from our queue, we can get its y coordinate as well. And then I also add this point here to the ones I print at the end. So I just print all the points at the end. Okay, so if it's a 2, then we need to remove from the 1s group. So if there are no 1s left to our right, since we're doing the sweep from right to left, if there are no 1s to the right, that means it's impossible. So we print -1 in return. Otherwise, we have the 1 to the right. We also have the match y, is what I call it, which is just the y of the 1 to the right. We can just remove that from our queue. Then we add the x and then the match y, and bring this up a bit. We add both of these as like a point because we're gonna, like us, we're gonna be at the y that matches the thing to the right, and then we're gonna bounce down from that. Okay, yeah, so I think that makes sense. So you'll have, like, basically, if you have a 2, you have you here, or you have this other thing here. You want to be at the same y as him. You'll bounce to him, you'll bounce down. You know this is a 1, which means this is empty, and this is also empty. This might be used other times, but it doesn't matter. Okay, cool, that's that. The last case is if it's a 3. So if it's a 3, first we want to prioritize matching with another 3 or with a 2. We'll do that if we can, but if we can't, then we'll match with a 1, because you can match a 3 with a 1, you just don't want to because it'll use up some of your space. So we try doing those, and we get match with will be the thing that we match with. If we can't match with anything, obviously it's impossible. And if we can, then we are at some y here. We're at some y. This other thing is over here. We want to add this point here. So that way we'll go like this. That's what we're looking for. So we add us, we also add this point. Okay, awesome. And then anything else? Yeah, each time I add a point, then when we go to the right, I start like higher up so I don't intersect with myself. I increase this y at most once per x so I don't run out of y positions. And then on top of that, I don't actually place it in this block if it's a 2. If it's a 2 and we've got like a 1 here, for instance, then I'll place the 2 here. Then it'll go like this. So yeah, that's the idea. Cool, that's problem D. Little careful. Also be sure to print yx instead of xy. That got me. I did pass B, thank goodness. Very good. All right, problem C, carrots for rabbits. Yeah, so this problem wasn't too bad. The idea, the thing to keep in mind is like x squared. If you have some number squared, it's like if you want to, yeah, so I guess let's just draw this geometrically, right? We have some square here. If we split this square number up into like 2 numbers that are very far apart, like this number here and this number here, we end up using a lot of space, but you can use a lot less space if you do something like this. I think that might be helpful. Like that's like an important thing to notice, right? So like the best way, if you have some number and you want to split it up into 2 smaller numbers and then square both of them, if you want that product to be, or that sum of products to be as small as possible, you want to split it up and like basically evenly. That's the idea here. So that's kind of just intuition for how squares work. Like they get bigger and bigger at a faster and faster rate. If you look at the graph of y equals x squared, it looks like that. So yeah, that's the idea. You want to like split it up basically evenly. Yeah, so what we can do is consider how much does it help us to give, I'm pretty sure I saw a video on how electoral college votes are distributed, and I'm pretty sure they do the same thing there. But with like a slightly different modification. But basically, the idea is like how much more will it decrease the total if we give this next split point to each caret. So if we know that, we want to give the split point to the caret that decreases the most, that like becomes, or for which it's most helpful. So initially, if we have a short caret and a really long caret, we'll give it to the long caret, and that will cut the long caret in half, and it'll decrease the sum of products by a big amount. But if we just have a short caret, then like we only want to start giving it to it when the rest of the carets are also very short. Once we have a square, if we know how many, or once we have some number, if we know how we're going to divide it, since we have to divide it into all integers, we want to do it as close to evenly as possible. So if we want to split this, let's say this is like 10 long, we want to split it into 3 groups. We'll split it into a size 3, and then, well, it'll be like this. So this is size 3, this is size 3, this is size 4. And it's always going to look like that. So this will be like the smaller of the two, and this will be the bigger. And the size of the smaller will just be 10 divided by this thing, which is the number of groups. This is the size of the smaller, so this is how you get this 3. The number of 4s there are will be 10 mod the number of groups. The reason for that is once you've done 10 divided by 3, if you have all of those groups, that'll add up to 9, right? So you have 1 left over. This 1 left over has to be part of a big group. And you want to split them out as evenly as possible, so you don't put them all in one, you split them out. So that's the number left will be 10 mod the number of groups, and then you can do it like that. So we know the cost, like this is the cost of some split point if we have, or this is the cost of like after you split up some segment, what its final cost will be. That's what this is. And we want to know how much does the cost improve if we give it one more split point. So we can calculate this in order 1 for the number of split points it currently has. Then we can say if we increase that number by 1, how much does it change? And whichever one changes the most, that's what we'll give this split point to. In code, it looks like this. First, let's go over this cost method. So this is, like I talked about, this is the size of the smaller group. The size of the bigger group is just smaller size plus 1. The number of bigger things we have is the total length of the segment, mod the number of parts. The number of smaller is, well, everything else is smaller. Everything that's not bigger is smaller. So everything that doesn't get the plus 1 bonus will be smaller. So we'll take the number of parts minus however many bigger things there are. That will be how many small things there are. Then we say, what's the total cost you spend on small things and on big things? So small squared plus big squared times the number of them there are. And that's how you calculate the cost. So the benefit of taking one more of these segments will be the original cost minus the new cost. We know the cost will go down, so it'll be this here. Yeah, okay. So what we do is like temporarily we'll add one more thing, we'll calculate the new cost, and we'll subtract it out so we don't actually modify it after this method runs. And then we just calculate the final thing here. This will give us we want to compare by whichever one improves the most. So that's why I do it like this. Priority queues put the smaller things first, so whichever one has the bigger improvement, I will put that, well, like that one is the one I want to pull from the priority queue first, which is why the order of these two things is backwards. So it'll give me the negative result. All right, awesome. Finally, we have the main method, which is just initially we build all of the segments, and then k minus n times we give one to whoever could use it the most. Then finally we just find the total and then print it out. So if you needed to, extracting the answer this way would also be very easy. Okay, awesome. That is problem E. I guess one more problem I should talk about is problem F, Well, I guess I'll talk about G2 because I have an idea for that. But the idea for problem F, ooh, I might go up in standings if people fail. It's possible. It's possible if people are failing B. Are any of my friends failing B? No. No, pretty much everyone is passing B. So I don't know. Maybe the circular case wasn't in sample somehow. All right, problem F. Yeah, problem F was math heavy. Or not really math heavy. There was no hard math. It was just counting heavy. So you have a string of zeros and ones, maybe like this. And yeah, I think this is fine. And you want to know for every substring, for every LR substring, you want to find, so maybe for this LR substring here, you want to find what is the longest range of ones. In this case, it's these two ones here. And then you want to add that to your total answer. So we'll try this for every possible substring, every pair of left and rights. We're going to find the longest continuous range of ones. In order to do this, we'll take a pretty solid or pretty standard approach, which is we'll consider how many times does each one get counted. So, or I guess it's a little bit more complicated than this. We'll look at a block of ones. We'll consider how many times does this block get counted. And there are a couple blocks we need to consider. So any block that's surrounded by zeros, or like the end of the board basically, like this, we need to consider this carefully. So the thing we should look at is how many times is like the left point of this possible, and also how many times is the right point possible. Left point, if we pick any of these left points and any of these right points, for example, then this block of 2 will be the longest possible substring. So this will be counted for all of these positions, and if we know how many times it's counted and we know its value, we can just multiply them together. That's the idea. Now you have to be careful here, because you might have an example like this where you have two things that are the same length. In this case, you need to say which one of them will get counted. You don't want to like overcount or undercount here. So they can't like both block each other basically. What I did is I said if you have, in this example, whichever one is to the left, that's the one that gets counted. So in this case, this one will get counted for any left point in this range and any right point in this range actually. So if we pick like this for example, the longest continuous range of ones will be 2 long. It'll be 2 ones in a row. And we want to take the first of those, which will be this right here. Okay, that's the idea. And that's like for the maximal ranges. There are a couple other ranges that we should consider. The first one is ranges that are like entirely inside some block of ones. So if you have a block of ones that's surrounded by 2 ones, those are pretty easy to count. We can say if we have some, like, let's say we've got some long block of ones, it's like 4 long. If we're looking for things that are of length 2, we can count this here, and this here. So they're just 4 minus 2 plus 1. Not plus 4, plus 1. There are this many things that are all length 2, so we multiply by 2. And for things within this block of length 2, this is the contribution they make. So it's that easy. For things of length 1, it'd be 4 minus 1 plus 1. You need the 4 plus 1 for like the endpoints. Times 1, because each of them contributes a value of 1. So in total, that'll amortize to order n, because if you have some big thing, then you might have to do a for loop all the way up to its size, but if you have some big thing, then it uses up a big number of positions in the array, so you can't do that very many times. So that's order, it's like linear in total. And on top of that, okay, so that's the first type of range, or the first type of range was a block of ones. You also can have stuff inside of a block of ones. There's also other stuff too, which is a bit more tricky, which is something like this. So you can have this 1 here, but you can use this 1. We already counted this 1 by itself, but you also might need to count something like this. In this case, this 1 gets counted. So we need to count some like suffix and also some prefix with something that extends outside this block. And if you count suffixes and prefixes, that's all of the cases. So yeah, you just have to, I guess, identify them and then figure out how do you count them. Okay, so how do you count these things? Well, basically, we can do two sweeps, one from the left and one from the right, and we can store those in memory and then look them up when we need them. So we can like kind of imagine we're doing two sweeps at the same time, and then we can just say like for this, or we can say for this range, when we were to the right, what's the first thing that like eclipses us in length? In this case, to the right, we want something strictly longer than us. So that would be this position right here has a range of like a run of 3, which is strictly longer than our run of 2. So we can get a pointer to this position with our sweep. And then we can say, okay, anything up to this plus our length, which is 2, we can count that. We'll also do this for every suffix. So this will really be, we'll have this pointer from the start of the range like this. We'll have it to here. But then for this thing here, when we are doing our sweep like this element will have a pointer to this position right here. So this element will know, okay, if you look at just like this part right here, from the 0 to this first 1, you want to see when is this eclipsed? Well, this one was eclipsed most recently by this. That's the sweep we'll do. Okay, so for handling prefixes and suffixes, it's a little bit messy, but we brute force the prefix, and that doesn't hurt our runtime, stays linear. Then we can say, when was this eclipsed? We can do this with info we collected during our sweep. And then we can say, okay, well, its left endpoint is fixed if it's a prefix, right? But its right endpoint can be any of these things. So we have, it can be 1, 2, 3, 4, or 5 things. Then you may or may not, depending on how you implement it, have to subtract 1 right here for double counting this thing here. So you may say, okay, instead of 5, there are only 4 right endpoints. And for each of these, we want to multiply it by the length of this prefix. In this case, it's 1, so it doesn't matter, but if it were longer than that, it would. All right, that's the idea. Okay, the final detail that I haven't totally covered is how exactly do you do this sweep? Well, we can notice that like what matters is like the first thing above some value. The first thing to the right above some value. So in order to maintain this, we can use a stack. And as we go right, as we go like this, when we're at some position, we'll say, okay, in our stack, we'll have this element here, because this was length 1. This here is length 2. This is length 3. So all of these will be in our stack. But once we see this here, this is no longer eclipsed by this, which means we can pop this off of our stack. So now our stack will have these two things which both have stars on them. And we can say, okay, well, this is eclipsed by the first thing in the stack. That's the idea. The code is very messy. There might be a better way of doing it, but I couldn't really figure it out. Yeah. So the idea is that first we'll do our sweep from the left with a stack. We'll keep track of when each position gets like beaten, basically. So for each position, one was the next best thing on the stack. And if it's a 1, that means we just need to update the tail length. So the tail length is like the number of 1s after it in the sweep, I guess. So the left tail would be when we're doing our sweep from, this one's from left to right, then how many things to the left are 1s? What's the continuous range of 1s? If we have a 1, then it's 1 more than the previous thing, unless the previous thing didn't exist, in which case it's just 1. And then we also want to remove things from the stack that are smaller than us. So if we're looking at stuff that's to the left, we want to keep things that are the same as us, because if we're on the right side and there's something that ties us to the left, then he's the one that gets counted. We only count ourselves if the thing to the left is smaller than us. So yeah, so as long as the thing is strictly smaller than us, then he's irrelevant. Or the thing to the left is, yeah. If he's strictly smaller than us, then we matter, so like he's irrelevant, so we remove him from our stack. When we do this, we know the stack will be strictly decreasing because we're maintaining it like this. So the first thing in the stack will just be the next relevant thing. So this is when we're beaten. In the other case, if we have a 0, that means we can add ourselves to the stack because this is like a new range of ones that's important. We do the same thing the other way. I won't talk about this, but it's basically the same. So now we do this other thing. Once we've done the sweeps, we do the counting. We brute force our start point, and now we take this entire range of ones. So we keep going as long as we have some range of ones. If it's a 0, we just skip it. So now we have this range end, which is just like the end of the range. And this part right here is just counting the stuff inside the range. So this is very easy. This is like case 2, like I mentioned earlier. Here we just multiply the size of the range by how many times it occurs. That's easy, I guess. Okay, now this is the part that covers the entire range. I'll talk about this, and I'll just skip this prefixes and suffixes part, because it's like the same thing, copy-pasted code, just slightly modified. But basically, we know the left endpoint will be when the left thing was beaten. That's like the farthest it can go. And the right endpoint is the farthest it was beaten when we did our sweep from the right. But these aren't totally true. So the first case is these could be -1s, which means maybe it might not be beaten at all. If that's the case, then like the start points will be 0 and n-1 respectively. If they're not -1, they still might matter. And in that case, like what we need to do is what our pointer went to was this first element here. But this first element and some more might be important. So really the maximum right endpoint is here. It's not right here, which is why we need to add something to it, because this whole range is valid right endpoints for which this group will be counted. That's the idea. So that's why we have to modify this. So we have the first legal start, we have the last legal end, the same thing. This +1 is because for things to your right, you'll tie them, and that's okay. For things to the left, it's not okay to tie them in order to make sure only one of them is counted. So, okay, good. That's the +1. I've explained that. Then these choices are independent, so we just multiply them together. We also need to account for the range size. Same thing for prefixes and suffixes. And then also, don't forget to use longs, not overflowants. Okay, very good. Finally, problem G. How do you do it? Well, I can give you a runtime that's all right. Maybe it's a little bit too slow. But the idea is, or I guess my final runtime is 10 to the 6th for like max n. Let me draw it a little bit bigger. 10 to the 6th times your 5 digits. Each of those I have a times 10 in, which that's kind of annoying. It's really times 10 plus 3. And then on top of this, I have a log k multiplier. So here's my final runtime, which is about 5 times 10 to the 8. Or, hang on, actually, this is 10 to the 9. Yeah, it's 10 to the 9 runtime, so you gotta get rid of this 10. And if you can get rid of the 10, then you're fine. I guess I'll talk about what I do, and then I'll leave getting rid of the 10 up to as an exercise to the viewer. Okay, so yeah, how do you do it? So the idea is there's this thing called 0k knapsack. Well, first of all, there's knapsack. Hopefully you know knapsack. The idea behind knapsack is you've got a bunch of things. Each thing has a weight and a value, and you can carry at most some total weight. You want to steal. You're robbing someone's house, by the way. You want to steal the most valuable total possible. Now, this is very difficult to do if you have values that are like doubles. It's probably not possible unless like p is equal to np or something crazy. But basically, the real way you do it is you do a dp. So you do a dp where your state is how much space do you have left, and then what item are you on. And you consider either taking the item or not taking it. Those are your two choices. So that's like a requirement for being able to solve this, and it's not too hard of a DP to do. But this is if you can only take each item once or not. You can also do this if you take each item an infinite number of times. So if you can take each item as many times as you want, like if there's an unlimited number of diamonds of a certain size, then you can take as many of them as you want, for instance. But the amount of space that's left is also limited. So you can't like take an infinite number of them, but you can take as many of them as you feel like, basically. In that case, the dp is also the same. The only difference is instead of your transition like before, it went to space minus weight, and then item plus 1. In this case, it'll go to space minus weight, and then you can take the same item again if you want. So that's the difference between the two. So this will be 0, 1 knapsack. This is 0, infinity. You can also do this thing called 0k, and that is you take at most k of a certain item, where k is some constant. And they can be different for different items, but that part isn't really super relevant. The important part is this. We can turn a 0k knapsack into a 0, 1 knapsack. So let's say you have like 10 of some item, or let's say you've got 64 of this item. You could take 1 of it, you could take 2 of it, you could take 4 of it, 8 of it, 16 of it, 32 of it, or you could take another one of it. And the important thing is, if you look at these, let's say, for example, you want to take 24 of these items. Well, 24 in binary is 8 plus 16. So instead of taking just 24, you could take the group of 8, you could also take the group of 16. Here we've split 64 up into log n different groups. Now 64 is a power of 2, so this is a bit easier, but if it's something like 68, so 64 plus 3, well, let's say 64 plus 5, actually. It's more interesting. 64 in binary is just some number. Then we have this plus 5. Well, 5 in binary is equal to 64 plus 1 plus 4. So we can have all of these things. We can also add a 1 and a 4. Now we have, instead of doing a 0k knapsack, which would be pretty time consuming, we can do just a 0, 0, 1 knapsack, but do it with slightly more items. That's the idea. Okay, so that's 0 and knapsack. That's that idea. Once you have that idea, you can solve this in a slightly better way. So the idea is we're just going to do a knapsack for where like the amount of money we have or the amount of weight we have is the sum, and the cost of each item will be like just the number that we're going to write. So if we split it up into digits, we're going to write maybe like a bunch of different numbers here. We've got like a bunch of different numbers we'll write. Maybe k equals 4. In this case, we're writing 4 different numbers. Each number has several digits. We're going to consider all of these like 100 digits all at once. So we'll say for the 100 digits, okay, you can take up to, like you can take, you can take 0, 1 or 2 of these, or 3 of these, because you can place a 3 here, well you can place a 0 here, you can place a 3 here, you can place a 6 here, or you can place a 9 here. And on top of that, you can do this up to k times, right? So it's like you can take 0 all the way up to k times 3. This is like 0k knapsack, where this is 0 and k is really k times 3. You can take any number of those, and that'll give you some points here. You can also take some number that isn't that for 0, and that's a bit messy. I guess there are easy ways of handling that, which is like if it's something else, you can take 0 all the way up to 9k. You can take multiples of 1 of this, and those are all free instead. So I don't know, maybe that's maybe there's an easier way of handling it than what I did, but yeah, that's the idea. So we're gonna do 0k knapsack. We do it 5 different times, or 6 different times, once for each digit, and then at the end, like we just compounded these answers into the same DP table, so it makes it easier to handle, and that'll give us our answer. So if you're able to solve that, you can solve both G1 and G2. Mine was a constant factor too slow, I think, or maybe a factor of 10 too slow. The constant factor may have been significant to get rid of. Yeah, so My issue here, I think, is that this for loop goes up to 10. This might be a bit slower than it needs to be. A bit too slow, I guess. But I don't know. Who knows? You can probably do you'd order these in some way, maybe do a query in order 1. So that's possible. If you had a min queue, you could use that for this. But I'm not sure. That solves both G1 and G2. I don't know the solution to G1 that wouldn't also solve G2. It seems pretty much the same. But there were some people who used it, so congratulations to them. And I don't know each. Awesome, yeah, and also this was very generous of the judges, so thank you for that. That was almost like a hint even. So I don't know, maybe I think no response would have been the right thing to say, maybe, but I'm not complaining. Like, it benefited me, so whatever. Cool, GG. For me, it looks like I passed system test for everything. Got plus 51. Not bad, not bad. Nice job, everyone who beat me, and everyone who went up, I guess. Good job for you. And, yeah, I thought it was a fun round. Thanks for watching, hope you enjoyed, and have a great day. Goodbye.